Okay, thank you very much, Sue. So Sue said, my name's Anthony. I'm an exploration geologist working for SRK Exploration Services. And this talk is on the geology and prospects of the Arabian Nubian Shield, so what we know so far. So the presentation will effectively cover an introduction to the geology of the Arabian Nubian Shield, as well as talking about some of the mineral occurrences and the prospects and mines within that area, and then also talk about some of the ongoing research as well that's ongoing in terms of understanding its evolution. Without further ado, so this map will be quite common, and I'll come back to this throughout the presentation. So this shows the extent of the Arabian Nubian Shield. It covers quite a large area, including the covered part, which actually isn't featured within this slide. It's more than 200,000 square kilometres in size, extending from north to south for more than 3,000 kilometres. It's bisected by the Red Sea, of course. I'll come back to that a little bit later on, which separates it out into the two distinctive parts: the Nubian Shield on the western side of the Red Sea, which occurs predominantly in southern Egypt, parts of northeastern Sudan, parts of Eritrea and Ethiopia, and then the Arabian side of the shield, of course, on the eastern side of the Red Sea, which predominantly covers, of course, Saudi Arabia, but also extends into the very most southern parts of Jordan. Now, the importance of the Arabian Nubian Shield has been known about for a long, long time. Actually, there's evidence of Egyptian mining back sort of as far as 6,000 years ago. In fact, some of the treasure that was associated with in the time of Antony and Cleopatra was known to have been mined from deposits associated on the Nubian side of the Arabian Nubian Shield. And the oldest workings date back to, that we know about, date back to about 4000 BC. Extending throughout eastern Egypt and the Sudan. Now, on the screen here is a fragment of the Turin papyrus, which is actually a very, very old, as you can see from the state of it, map, topographic map essentially, but actually you could argue that it's actually one of the earliest effectively geological maps as well, because not only does it describe the topography of the area, it also indicates, to a crude extent at least, the types of geology that occur within this particular area and where mines have been located. So it's been known about for a very long time. So the geology of the Arabian Nubian Shield, or the ANS, comprises a number of distinct lithotectonic blocks and arc terrains. And these have essentially been accreted together, and I'll talk a little bit more about this later. These have been effectively accreted together to form a number of distinct assemblages, which actually makes it overall very prospective as a region. And they've been deformed and sutured and folded and intruded by various plutons, younger calc-alkaline intrusives during the Pan-African orogeny. And as I say, this diverse and quite extensive geological history is actually one of the reasons why this particular area is very prospective for a number of different types of deposit types. So if we look at how the ANS actually formed, so the Arabian Nubian Shield was originally part of a supercontinent, one of the earliest supercontinents called Rodinia, and this was in the around about 1 billion or so, 1.5 billion years ago. And this went through a period of breaking up, and effectively there was a series of rifting events within Rodinia that caused it to fragment. And during that fragmentation, a number of juvenile crust microplates were created during the period, as it says on the slide, I hope you can see, around about 870 million years ago. And effectively what happened is that all of these microplates, or back arc terrains, as they're properly called, were then crushed together, in a sort of reworking of the lithospheric plates and in a collisional boundary, and this formed part of the East African origin. And associated with this was the intrusion of various granitic plutons around about 650 to 600 million years ago. Now this continued, the collision of this area continued, and as it says, under the the fourth image down, effectively you had a series of mountains effectively being produced, called a massive uplift caused by the plate collision, and this led to various tectonic events and various significant faults being produced and orogenic collapse. And the final assemblage of the Arabian Nubian Shield was part of Gondwana, which was achieved between about 550 and 520 million years ago. And this was created as part of what's called the Pan-African orogeny, which is a regionally significant period of deformation and shearing throughout the African continent as it was at the time. And as part of this orogeny, the whole area was uplifted quite significantly. In fact, it's been shown, there's evidence to show that parts of the shield in Eritrea are thought to have been uplifted by between 30 and 35 kilometres, so significant uplift. And of course, a lot of that has since been eroded and has produced a number of sedimentary basins. And the most recent, of course, event is the rifting up down the Red Sea, and this started about 31 million years ago, roughly, and is still taking place now, of course. And the Arabian Shield is moving away from the Nubian Shield by around about 16 millimeters a year, so relatively slow. It started off quite fast. It's slowed down a lot in more recent geological times, but it's still moving apart, of course. I appreciate that this is quite a busy map that you may not be able to see fully from the back, but it's just evidence to show you the number of tectonic sutures, particularly on the Arabian side of the ANS, and these mark the division between lots of tectonostratigraphic units. And these are important features when it comes to understanding the location and the formation of certain types of mineral deposits. On the right image is another example which actually shows in a sort of reddish colour the distribution of various or thin collisional granitoids which have been intruded during the collision of the various assemblages that made up the original ANS. And it's important that, and the thing I should emphasise is that these can be dated, and I'll come back to this as well, because they're actually, the fact that they can be dated is very useful to us because we can determine the evolutionary history of the ANS. So this shows this couple of maps. They're pretty much identical. The one on the left shows you the small yellow circles show you all of the different occurrences that have been identified. And these occurrences are predominantly for orogenic gold type of deposits or occurrences, as I should say, and VMS or volcanogenic massive sulfide type of occurrences. The map is actually taken from Johnson et al. 2017. The map on the right-hand side indicates in the form of stars some of the more significant deposits that have been located. But it doesn't show, and as I say, these are predominantly orogenic gold and VMS style deposits. It doesn't show, however, the other deposits which occur within the ANS, which include things like phosphates, iron ore, titanium, and many others. And some of the important ones that I'd like to highlight, you probably won't be able to see right from the back, but they include deposits such as, for example, as the Cauvery deposit in southern Egypt. You've got the Maha El Dabad deposit in Saudi Arabia, the Legadembe deposit in Ethiopia, and the Tulu Kapi deposit in Ethiopia, and many others. But comparatively speaking, the region is relatively underexplored when it comes to if you look at the size of it in comparison with other types of shields around the world. So if you look at, for example, the shield in Western Australia, you've got a massive mining industry there, for example, but actually in comparison with the AMS, you've got a much less well-developed industry with significant potential for future discoveries. So the main types of deposits that are attracting the most interest within the AMS are predominantly orogenic gold and VMS style of deposits, and a couple of diagrams on the screen. For the geologists among us will be familiar with this type of model, how orogenic gold deposits form, typically quite deep within the crust, associated with large-scale suture zones and fold belts. And the VMS deposits, of course, typically associated with back arc or rifting type of environments, exhalative type of deposits, associated with quite high-grade copper and zinc type of deposits. Now, many of these, of course, have been deformed, so quite significantly since they were formed, but this is part of the challenge of exploration, of course. However, in addition to the orogenic and the VMS style of deposits, one thing that's one company in particular I'll talk about in just a minute that has been quite of interest, particularly from an academic and exploration point of view, is the fact that there's now been a confirmed discovery of a porphyry deposit within the AMS, and this is called Gibberson. I'll come on to this shortly. There are other deposits within the AMS as well. I've listed these on the right-hand side of the slide. I would emphasise that there's probably limited economic potential for these at present. However, that said, nobody ever thought to expect to see a porphyry deposit either. So there's a good chance, of course, that some of those deposits are just waiting there to be discovered. So Gibberson here is the porphyry deposit I just mentioned. I don't know whether you can make out where it is, but there's a small blue box in a sort of a red part on the Nubian side of the shield. This is being explored by effectively a part of Qatar Mining. It's actually Qatar Mining Sudan Limited. They're based in Khartoum, but they have exclusive access to the exploration of this particular deposit. Now, exploration has been going on there since 2013, but it was only identified really as a porphyry in late 2014 or early 2015. And in December 2017, after a reasonably significant drilling campaign, they actually published their maiden resource estimate, which, as you can see on the screen, it's not enormous in terms of porphyries, but it's significant, particularly for the region. About 250 million tonnes at, say, 0.4, 0.5% copper, using a cut-off grade of 0.2% copper. A little bit of gold in there as well, not massive, but a little bit. So Qatar Mining, or QMSD as they're actually known, have undertaken, as I say, quite an extensive drilling program at the moment. They've got a drilling program that's ongoing for another 133,000 metres of combined RC, or reverse circulation, and diamond drilling. And they're scheduled to release their initial pre-feasibility study, or PFS, scheduled in late 2020. There's a couple of examples of the exploration that's ongoing at the moment. Always nice for us exploration geos to see a drill rig in action. Not quite so nice to see that big plume of fine-grained gold or something disappearing up the stack. But anyway, there you go. So this is the drilling program that's currently in operation there. The black lines with dots are the drill holes. The green lines represent a series of faults or dikes that they've identified in the course of their exploration, and the red lines indicate a couple of cross sections. This has been taken directly from QMSD's website, and as looking at the section 2100, as they've recorded it in the extreme, what's that? That'd be the east of the deposit. This just gives you a nice indication of some of the drilling that's happened there, with the red indicating more than 5,000 ppm or more than 0.5% copper. So nice high grades at the surface, predominantly oxidised material with more unoxidised sulfidic material down below. Now that was just one example, of course, and as I said earlier on, there are a number of quite significant deposits that have been identified in the ANS, although it's not as well explored as perhaps it could be. I've indicated in the chart on the left here, the reds are operating mines. It's probably a little bit too small for some of you to see, but I've highlighted just 3 of these on the chart on the right hand side to give you an indication of the size of some of these deposits. So Cauvery, I mentioned earlier on, was probably the first major and significant deposit to be found on the Nubian Shield side. This is an orogenic gold style of deposit with a surface resource of almost 200 million tonnes at 1.3 grams per tonne, with an additional underground measured and indicated resource of about 30 million tonnes at 5.2 grams per tonne, so nice and significant. The Legadembe deposit in Ethiopia, again another orogenic gold deposit, a little bit smaller, 66 million tonnes, but a little bit higher grade, 3.7 grams per tonne, with again a nice underground potential as well. And Bisher, of course, different style of mineralisation, a VMS style of deposit, measured in indicated resources of about 26 million tonnes. These figures are taken from various press releases that companies have issued. So, coming on to the end of the talk now, but before I do, I think it's important to say that obviously I emphasised at the start of the talk there is significant potential for exploration and discovery of a variety of mineral deposits within the ANS. It's, in my opinion, definitely underexplored, and it's got a lot of potential. But in terms of the ongoing research and understanding, there are a lot of people looking into how the ANS actually formed and the timing of when all of these collisional events actually occurred. And this is to better understand have a better understanding of the crustal evolution, which will ultimately help us, of course, understand how things have formed up and ultimately indicate where mineral occurrences will be found. If you think about it from what's called a mineral systems approach, and I won't talk too much about this now, partly due to time, but also because I know that both speakers after me are going to be talking about this in a little bit more detail. But essentially the mineral systems approach is a relatively new way of thinking, and it looks at things on a large lithospheric scale. So it looks at how things have evolved over time, and how plates have evolved, and the formation of a region. And it understands that you're effectively trying to concentrate the fluids over a regional scale, and that mineral deposits themselves represent the focal points for the concentration of those fluids. And to do this, you have to look at the evolution of the area on a very large scale. So people are looking at this now, and in fact there's a recent paper that was published by Zahir et al. Just in this year, 2019, who's looking at the shearing and the delamination of the subcontinental lithosphere, and his conclusion was triggered by a change from transpression to extension. So new exploration techniques or models are constantly being evaluated and looked at in more detail in response to this evidence, using things like geochronology, for example, dating the granites, using Zarkon data, for example. And there is significant potential for additional discovery of deposits undercover. For example, the big sedimentary basins immediately on the eastern side of the Arabian Shield, a big part of the ANS, they have additional exploration potential as well. Of course, they could be covering concealed parts of the ANS, but they also could be hosting themselves and mineral deposits, some of which I mentioned a little bit earlier. So, in conclusion, I hope that you will see that the ANS, certainly in my opinion, is extremely prospective and relatively underexplored in respect to other shields around the world. There have been significant deposits that have been discovered. However, there is very high potential for further discoveries for a variety of techniques, not just including orogenic gold, VMS deposits, but now also porphyry and the potential for things like pegmatite veins, polyphil chromite, and other types of deposits. And ongoing research into the evolution of the ANS is, in addition to the obvious potential that the ANS provides, is stoking a renewed interest in the region. So if you've got a spare few $1 million around and you're interested in the exploration game, there's certainly worse places in the world than I would look. So you know, it's something to consider from an exploration point of view. And you know, if I was in that position, I would certainly be taking an interest in doing some exploration in the ANS myself. So thank you very much for your attention. And I don't know, do you want me to ask some?
Yeah, of course.
All right. So my name is Simon Larch. I'm a researcher at the Natural History Museum. First of all, maybe thank you for having me here. It's quite nice to be able to present your work to a more industrial focused audience, or more applied audience. So I'm mainly working on the FAMOS project, which you see the nice logo on the bottom right. And what I want to talk about today is fertility indicators for porphyry deposits. So only one deposit type, one of them that Antony has talked about. And so I will mainly concentrate on Zarkon in this talk. So the general idea of fertility indicators is that you analyze a certain rock for whole rock, or in this case zircons from a certain rock, and you try to understand whether the magma that these zircons crystallized from had the potential to form one of these giant economic deposits, or if the magma seemed rather barren or uneconomic and we can just walk away and go somewhere else. But before I concentrate on that, maybe I quickly want to introduce the load group. So at the Natural History Museum and also at Imperial College, we have the load group. Don't know how many people are aware of it. So the museum actually offers consultancy work to companies, and we also have our own lab in the basement, and we mainly do porphyry vectoring, but also porphyry fertility. So we kind of combine research and also services. And the lab is sponsored by the companies at the bottom. But just to introduce you to the FAMOS project. So FAMOS or famous, it's still debated what it's pronounced, right? But I say FAMOS. And it's an acronym from arc magmas to ores, and that's essentially what it is. So it's a big consortium of universities in Britain, also some international collaborators. We have companies, we have independent consultants, and we meet half yearly and kind of compile our results that we've gained so far. And the ambitious aim is to get better understanding about the transcrustal processes that eventually lead to the formation of porphyry copper deposits. So this is a very schematic overview slide from one of the review papers of porphyry deposits. So you see essentially the porphyry deposits and epithermal deposits form at the very top. But nowadays we believe that actually a lot of processes all along this cross section are important to actually form the magmas that can source these deposits. And two things that I want to concentrate on right now is one of the main aims is to understand why these deposits seem to form in a very tight temporal frame, so within certain arc segments and special time frames, and also why they are spatially restricted. And we don't only want to understand it, but we can actually also use it a bit for the second aim that we have, which is trying to integrate the different results that we get to hopefully develop new fertility indicators that might be helpful to industry and exploration. So maybe just to slightly or very simply explain the concept of fertility. So this is a very simple sketch of how a lot of people believe porphyry systems work in the upper crust. So this is just the upper crust. So we may be in a typical Andean Cordillera and arc style, and we have an upper crust, a magma reservoir that's sourced from below. And if we just crystallize a magma reservoir, we get something which is similar to a granite, maybe more intermediate, but equigranular. If we If we are unlucky, in some cases we get major eruptions from this magma reservoir, or if we're very lucky, from an explorer's point of view, we can form a copper porphyry deposit from it. And the idea of fertility is that we can analyze each of these rock types. So we can, I mean, if we see the porphyry itself, it's quite easy to find the porphyry. But we can also analyze equigranular host rocks or country rocks, or we can also analyze volcanic deposits, and we want to try to understand, and from that information we can say something about the magmatic plumbing system that sourced them. If the same plumbing system had the chance of forming a deposit, or is most likely completely barren and it's not worth looking at any further. And of course we are not the first people who do this. So this is a very popular paper from 2016 from Lu et al. And from now on I will only talk about zircon fertility. So we are only talking about the mineral zircon, which we extract from the rock and analyze. And they made this compilation from global data sets, and they found that, so this is called the europium anomaly, and this is another geochemical indicator, it's cerium over neodymium over yttrium. It's not that important what they mean, but what they found is that most of the systems associated with porphyries seem to be plotting in the top right field, maybe also in the left, but always in the top half of this diagram. And all the systems that seem to be unassociated with porphyry deposits plot on the bottom. So if you go to the field and analyze a rock and you find these kind of signatures in zircon, people get very excited. And it works reasonably well. So all the porphyry districts in the world seem to be plotting roundabout in that area. So I will today talk about Rio Blanco, Los-Bronces in Chile. And so that is the data that I generated from the all associated porphyries, and you see it fits very nicely with the data from Lu that he compiled. But then what is not really discussed in this paper is also often neglected in other work, is that there are a lot of false positives. So this, for example, is the Fish Canyon Tuff, which is a giant ignimbritic eruption in the central US, and it has nothing to do with any kind of porphyry mineralization, but it seems to plot in the very fertile field. And similarly, when you go to northern Italy, to the Adamello Pluton, you also get zircons that plot in the very fertile field, and I guess you can't see it, but the cows seem very happy here, but there are no happy miners anywhere around in northern Italy. So what we try to do is maybe kind of advance this approach and maybe make it a bit more robust, and maybe try to see how we can kind of add information to this or get more information out of the data that we have. So what we try to do is first concentrate on one district and try to, a bit to what Anthony has elaborated on, try to understand the temporal evolution of the system and what makes the porphyry forming episodes so special to the other ones, and then see to how we can maybe apply that to a more practical perspective. So the location that we chose is Rio Blanco, Los-Bronces. So I should mention we are very happy that Anglo-American is also a collaborator in the project, and they granted access to the deposit. And one of the reasons for choosing it is that it's one of the largest deposits in the world. It's in the top 2 or 3, 4 porphyry deposit clusters. And you will not see it on this map, but it's located exactly in this square. So for comparison, this is Santiago, so that's 8 million people. At the moment, a lot of them are demonstrating. Over this side is Argentina, and this is the Andean Cordillera. And actually, in this segment of the world, on this part of the arc, a bit to the south and a bit to the north, you have a lot of prospects and also large deposits. But this, together with El Teniente, is one of the biggest ones. So if we zoom in and look from the bottom left, from the southwest, you see here, this is the Los-Bronces mine from Anglo-American. Actually, on the other side, here's the license area border, is the Codelco Andina mine. And you see it's in higher elevation. But what was important for us, going back to this image, I will show you a geological map of this area now, so I don't know if you can see the scale. This is like 40 times 20 kilometers. And this is dominated by Eocene to early Miocene volcanics that are intruded by Miocene to Pliocene intrusions, and those host the porphyry mineralization. So actually, when we zoom in, everything in gray are earlier volcanics, which I will not talk about today. and everything in pink and colorful are intrusions. And you see the big deposits are here in the eastern segment. But what this allows us is to take samples from the entire district. So in gray are a lot of equigranular rocks that I sampled, slightly different compositions. Sometimes you see contacts. I mean, it's mapped as a pluton, but typically these are kind of incrementally assembled bodies. Also sampled a few porphyries that were identified by exploration but are sub-economic or close to barren, which are good comparators. And then, of course, also sampled the porphyries within the Los-Bronces district. And we did whole geochemistry as well, but I also extracted Zarkons from most of these samples where I could. And then again, you can make these fertility diagrams, again an X and Y plot, and this one is similar to the previous one I've shown you by Lou. And it seems to distinguish sub-economic and productive relatively well. So everything in orange are porphyry or zircons from porphyries that are associated with mineralization. Everything in gray is the equigranular barren host rock pluton. And in brown you have the sub-economic porphyries. And you see in European anomaly space and then the cerium factor space, they seem to be separating out relatively nicely, with the exception of this one sample, which seems to straddle down here. However, we have the same problem again as we had for the Lou data set. So actually the Anglo geos then tried to apply it to a different setting, somewhere completely different in the world. And the systematics were somewhat similar, but they had different absolute values. So maybe within a district, the kind of image is the same, but it shifts maybe down over to the left or to the right. So sometimes productive porphyries will fall in the sub-economic field and vice versa. So what can we do about this? How can we make this more reliable? And I strongly believe that we can actually use the temporal information of the zircons as well. So this is just a Y plot, so there's nothing on the x-axis. And this is time, so we go from 20 million down to today. In blue, this is the rhenium osmium date, so the mineralization of the just sub-economic San Manuel porphyry, which is quite big, but too deep. And in orange, you see all the compiled dates from Rio Blanco Los-Bronces, so the 200 million tons of copper. And if we plot our samples, so each one of these bars is the zircons from one sample, all the dates grouped together, and an age is calculated from it, and that's a reasonably good estimate for the emplacement of that certain rock or crystallization, time of crystallization. And you see that in gray again, the equigranular ones, they seem to span a certain time scale, and also in brown you see the sub-economic porphyries kind of interspersed in the middle. And there seems to be kind of incremental assembly of this body over more than 10 million years. And what's striking is that all the porphyries seem to intrude towards the very end. So like the last 2 million years of magmatic activity within this small area in the world is the time when all these deposits form. And it has to be said that this is not a unique observation. I'm not the first one who sees that. So in a lot of the other big porphyry districts, especially in the Andes, but also elsewhere in the world, you often have, you see intrusive, sometimes also volcanic rocks, but mainly intrusive rocks, kind of predating the large porphyry forming event by 5 to 10 million years. So how do we combine this with the geochemistry? So I tried it, and the plot is a bit scattery and hard to read, but I hopefully can show you what I want to say with it. So this time is on the x-axis. So again, it goes from 20 to close to today. And these are individual zircon data spots. So each one of these is one laser spot in the zircon. And I plot the uranium lead date versus the geochemical trace element information. And you see that there's a lot of scatter. So everywhere you have higher spots, lower spots, which is completely normal. But I think it is quite striking that more or less with the start of the San Manuel, or with the intrusion of the San Manuel porphyry, and slightly later when the main mineralization is formed, you have these shifts to different values. So you have increases to higher hafnium, you have kind of a jump to higher europium anomalies, europium anomaly values, and you shift downwards in titanium. And The easiest explanation for that is that you have changes in the magmatic plumbing system in the deeper crust, so you have a different fractionation assemblage. But that's not what I want to talk about today. What is important, and I'm coming back to one of the points I made on one of the first slides. So, as I said, in this project, we try to emphasize on the temporal and spatial concentration of these deposits. And I would argue the temporal concentration we have, or the temporal restriction of the formation or potential to form these giant deposits is actually quite nicely seen in this diagram by these shifts. So you need a certain kind of magma chemistry that resulted in the crystallization of these zircons to potentially form these giant deposits. But now a lot of people will say, well, you analyzed the biggest porphyry deposit cluster in the world. Of course, you see something. How do we use that if we want to find deposits? And of course, it hasn't been tested so far, and it's not very robust. But I would argue, based on the information that we have, that if you do regional scale exploration and you get a regional data set, may it be sampling in different locations, or maybe even stream sediment sampling, because zircon is always in the heavy mineral fraction of stream sediments. And you see a multi-million year continuous zircon growth over multi-million years, and certain geochemical shifts which indicate fertility towards the very end. That might be a good indicator for a large deposit, or for the potential of the area to have formed a large deposit. So just to illustrate, this is actually something I want to try to do next year. This is the same image again as from the start. Again, we have Santiago. This is where the deposits are located, and it's now quite hard to see because the screen is not very big. But you have a lot of streams and rivers coming down. So what I would like to try is go to where the streams enter into the main valley, take stream sediment samples, and I believe what we will see is that where we have these gray dots, you will see a more or less flat zircon distribution over a certain amount of time, but you will not have the record of these porphyry zircons within the samples. Whereas all the rivers that drain this area hopefully will show this multi-million year record with increased fertility indicators, and then you can move forwards. And I would argue this is hopefully it will be able to demonstrate that you can kind of vector towards the deposit just by normal stream sediment sampling. As I said, it's early stages, and it's not 100% robust now, but I think this might be at least an early stage exploration tool that maybe could be applied in the future. So that's that for me. Just my quick conclusion, maybe take home messages. I believe when you analyze zircons anywhere, which is conventionally done in exploration projects nowadays, I think it's important to integrate the temporal information with the geochemistry. I think often you just plot the geochemistry and then you get an age, and you don't really combine the data sets together. I mean, many people have shown that. We also see in Los-Bronces these giant porphyry deposits or deposit clusters formed towards the end within an arc segment. So maybe should have mentioned, but after this, all the magmatic activity has more or less changed or switched about 10 kilometers to the east. So at the moment there are no volcanoes, or we don't know about intrusions, of course, but there is no volcanic activity here at all. And we can combine this information with the fact that often within a certain segment you can distinguish geochemically between fertile and unfertile, productive and unproductive, and we can use these geochemical shifts to say something about hopefully say something about the potential fertility of an area. And I think that maybe I think mainly the tridal might be the most useful ones, multi-million year zircon records that culminate in fertile signatures might be at least a promising sign for porphyry exploration. So that's that.
Right, good evening everybody. Yes, my name is James Gilbertson. I'm the MD of SRK Exploration. So we're the division that works with the early stage projects within the SRK group. When I was asked to put a talk together, I was asked to put something together about an area of the world that we feel is particularly prospective for exploration, etc. And I wanted to turn it around a little bit and say, well, in actual fact, one of the main areas I think that we need to be looking for in the future is not necessarily a jurisdiction or a region, but it's actually undercover. So that's what I wanted to talk about today. But first, I'm just going to briefly discuss the concept of exploration search space. There's a really good paper, if anyone wants, they can come and find me, from John Ronsky that sort of frames this. But if any of you have ever done any sort of economic modelling of the exploration industry, you'll soon come to question yourself, or to question the viability of exploration. But the whole point is that you're missing, there's a few things you're missing here. You're missing that there's a complete non-correlation between the inputs, the blood, the sweat, and the tears that you put into exploration, and the outputs, i.e. discoveries. And there's a complete bipolar distribution in terms of exploration success. You have a couple of companies, a couple of groups that are phenomenally successful, and then a huge number of people and groups that are not. Which also asks you the question as to why are these people or these groups particularly successful in mineral exploration? And it often comes around to this concept of search space. It's doing your exploration in the right search space, in the right areas. Now, that could be an area, that could be a concept, that could be undercover. Exploration is quite unique in that it involves the search through a defined parameter space. That's your exploration search space. The main points with a search space is in the exploration arena is it is progressively becoming exhausted. We are one of the few industries, if not the only industry, where the better we get, the worse results we get. Because we found it all. So we've got to have that in your mind. You also find that the largest deposits are always found first because they have the largest signatures. And there are a key number of disruptors in this sequence of finding your search space. Now, it could be new technologies, and there's some really good historical results about certain technologies coming in and suddenly having huge discoveries in Canada and Australia and that. New mining and processing technology, which is another way where we can actually start to process something that historically hasn't been able to. New geological concepts, and I'll discuss one of those in a minute. New geographies is a fairly easy one to understand, where a certain country opens up and people come in and new discoveries are found in those areas, and that's a very key exploration search space, particularly for the junior sector. And then, of course, new markets, if new minerals such as rare earths 10, 15 years ago. So the adage really is that the juniors focus on one particular new search space, and that is jurisdictional search space, or frontier ground, as I would call it. So they are the people that will be the first people into the Central African Republic or Eritrea or these countries as and when they come in. And that's how they differentiate themselves. That's how they find their discoveries. Majors are going to be looking at other types of search spaces. Where have people not looked at before? And one of those is key to us is undercover. But I also want to talk about why I don't necessarily believe that's true, and I feel that the junior sector can work undercover, and it's through the adoption of some new ideas and new innovation. So the issue we have is most of the world today looks like that. How the hell do you do any exploration in that when you're looking under significant sedimentary cover or recent cover, Arabian sands and the likes? Very briefly, it does come up this image after a while.
Press it again.
Do I need to press it again? Oh, yeah, there you go. This map shows, just graphically illustrates where in the world we have hard rock, where we have exposed rock, and that is pretty much hosts 95% of the world's deposits today. The rest is under some form of cover. And to say that there's nothing there would be ridiculous. So we've now got to start thinking about how can we work in this search space. This is another trend that I'm sure a lot of you have seen. There's a definite increase a trend for increasing the depth of discovery. I've recently been involved with a new porphyry discovery in Ecuador that's 1,500 kilometers. 1,500? I'm sorry. 1.5 kilometers of depth. So these are the sorts of depths that we're now talking about in terms of discovery. So how do you hunt in this new search space? And I break it up into three main categories. Is adoption of new concepts, and I'll talk about that in a minute. We're going to be talking about the mineral systems approach, which the last two speakers have talked about as well. New technologies, and that is I'm going to talk here about ionic geochemistry, but there's a whole host of new exploration technologies that are coming together. And then what I term is data integration. Now, some of that can be such things as machine learning and data science. Now we're dealing with larger data sets. But it can be just simple things by putting two bits of data together that people haven't done before. We just heard from Simon about the idea of putting age data and your geochemistry together and actually seeing what that gives you. And there's a lot more of that happening now, I think, in exploration. So if we just move on to the mineral systems approach. So what is the mineral systems approach? Well, fundamentally, it's not that new. It's something that certain people have been working from the 70s. Western mining in Western Australia sort of ran with this concept and were exceptionally successful. But it's only really recently that people are starting to think about it more and looking at deposit models. Well, actually turning away from deposit models. That's the whole concept. We don't look at deposit models, we look at the plumbing systems. And we understand the much larger systems here. And through that, we find major discoveries. And you'll find that most major mining houses now have whole divisions that are devoted to the mineral systems modeling. By and large, it's just good earth science, first and foremost, and it's born out of this idea that the majority of the world's crust is actually underplated by fertile lithospheric mantle. Even juvenile terrains actually have some aspect of fertile mantle, and that we consider the mineral systems approach as a sort of a bottom up, and it's how do we get that fertile material or aspects of that to the surface. Deposits are the result of a mass energy transfer through very large scales, lithospheric scale. So we're starting to look at lithospheric structures, lithospheric scale structures, but lithospheric scale alteration in inverted commas. And that we're dealing with complex dynamic systems. The deposit that we mine today is a fossil. It's a fossilized example of a dynamic system. So we should be thinking about it as a dynamic system. We shouldn't be thinking of it as a static system, which is historically has been used in the past. Mineral systems approach is also fluid-centric, and I'll explain that in a little bit in the next slide. But we try to look at it in fluid mechanics and how things move and how does the plumbing systems work. As I said it before, it's a bottom-up scenario, so we're trying to look at mantle lithospheric crust and understanding how we get that material up. There are groups around the world, Graham Begg actually in Perth has got a great product for this, who map out the world's, they have a Google map, not of the surface, but of mantle, of lithospheric mantle. And understanding the framework of that has helped phenomenally in defining fertile camps for various deposit models. Let's try and think the next point was. Yeah, so one thing we have to think the mineral system approach gives us is we look at specific geodynamic periods, is that temporal approach again. And it provides us with critical targeting parameters. This is the slide I was going to talk about. So this is just a brief history. This is actually again from John Ronsky on how we viewed exploration historically and how we did exploration. So we started off with ore specimen centric. So this is your prospector going around kicking up a piece of rock, and he picks up some chalcopyrite and says, right, I'm in a copper belt, and that's what focused our exploration. That was back in the 1900s. Then we started to understand that things actually form in host rocks. So we need to try and understand the geology around us. Are we in the right area? So exploration focused on that. And we're currently in what we would term as a structure and chemistry centric exploration. We go out there and we spend an awful lot of time trying to understand the structural framework, and we look for geochemical signatures, we look for anomalies. What the mineral systems approach is trying to do is take us on a little further along the journey and look at fluid and physics centric. So this is trying to understand, as I say, the fluid systems and understand the physics of getting sufficient fluid through the crust to provide us with the deposit that we find today. What are the advantages of the mineral systems approach? Well, it's a where, not how. So it does allow us to help focus. It really does. If you spend the time on a mineral systems model, you can get it. Cam McClay says this. He says you can get it almost right, but you can be very wrong in the next. Let me get this the right way around. If you get the mineral systems approach right at the early stage, you can get it wrong in the next stage, but still find a discovery. It focuses you on a camp scale and then a deposit scale. It's a scale approach. It's not constrained by dogma, geological dogma. We don't try and hold ourselves to this is the classic VMS model, this is what we must be finding, or the Porphyry model, or an orogenic low gold. It opens up the concepts of being able to look at things slightly differently. Rapid ground reduction, which again, in exploration, we all heard the adage of 1 in 1,000 or 1 in 10,000 occurrences become a mine. What we want to do is we don't want to concentrate on the 1, we want to concentrate on the 999 and quickly reduce them. And this approach allows us to do that. And I've highlighted the next two because this is interesting for this search space that I'm talking about, which is the undercover. It helps predict the presence of fertile ground or prospective ground at depth or buried, because it's a 4D approach. We tend to unravel the structural framework and understand where things were during certain epochs that we know to be prospective. This is briefly the diagram that's often used, where we try to look for fertile ground, favourable whole lithospheric architecture, the right geodynamics. That forms a deposit. On top of that, we then need preservation. And I won't go into that in a lot of detail, but there's a lot of information as to how we select those. This is just a brief overview. So, favourable architecture. Understanding the whole lithospheric architecture. Gravity data is fantastic for this. This is an example in the Carlin trend and the Broken Mountain Eureka trend, where if you look at the geology sense, there's no concept as to why we get this trend of Carlin deposits, but if you actually look at the Bugel anomaly and corrected Bugel anomaly imagery, we actually see that there's two very distinct whole lithospheric scale structures that are controlling the implementation of it. Fertility, understanding if you're working in a particularly fertile ground. This crosses over a few of these, but this is, for example, why are we particularly fertile for porphyries in that region of Chile, what we just heard from Simon. There's some discussion as to why certain areas of Central Asia are particularly fertile. Is it something to do with that particular mantle lithospheric block? So understanding the fertility and where you sit in that. And then geodynamics, understanding that major deposits tend to happen at changes in geodynamics, changes in stress. We heard just now that porphyries tend to happen, or the large porphyries tend to happen at the end. When we look at it scaled age data, it tends to happen to be the last thing. So why is that? Is there a change in structure? There's a change in geodynamics that cuts that system off. If we wrap those two up, then we've got to start thinking about preservation. And then understanding again that major deposits tend to form on major structures, and those major structures quite often allow for downwarping and therefore preferential preservation. So you tend to get larger deposits preserved. We certainly see that in the porphyry environment again, if we look at old porphyries, such as those in Central Asia, and again in the ANS, it's the larger deposits that seem to have been preserved in ORP. What do we get out of the mineral systems approach? Well, we get a 4D mineralization predictive model. This is just an example from a fairly mature camp. This is from St Ives Gold, a mineral systems model over, as I say, a mature area in Western Australia. Camp definition, targeting, very specific camp targeting, and we get a scaled critical targeting criteria that we can go out there and try and map. Do we find particular structures? Do we find particular styles? And by, as I say, spending the time on this 4D model early on allows us to actually align our exploration on the ground a lot more robustly. I'm going to move on to the second one now because I've got quite a lot of material to go through. Ionic geochemistry is a new, again, inverted commas, new technology that I think can be used to help us in this search phase. I don't know how many of you know about ionic geochemistry. It's in the 80s. It was conceived and it was very much seen as a wacky science. It's now starting to be accepted, and certainly major mining houses are now using this. It's actually born out of quantum mechanics, quantum physics, but it's the movement of ions up a vertical column rather than elements. And what's allowed us to do that is the reduction or the increased precision in assaying. So we can now assay down to ppb level very, very comfortably. That allows us to pick up these ions. The interesting thing about these ions is that they travel up this vertical column. The best way of thinking about it is osmosis, and they travel up fast. And I'll show you how fast in a minute. But when they get to the surface, they rapidly are absorbed into compounds, so you don't get them. What that means is, unlike classic geochemistry, we don't get this halo, we don't get this downwarp, we don't get movement of those anomalies. So there's often soil anomalies, gold soil anomalies, that are unproductive because of the regolith that's moved, or it's transported regularly. This gives you a very clear signature directly above a mineralization. It's very subtle, but if you actually cut out the background and if you do a bit of data science underneath and you do your principal component analysis, they actually can cut that out and you can show them, and they can really come out as bullseyes. In terms of speed, this is an exercise that took place in Indonesia, where we had two gold hosting veins that were covered by a 1.5 meter thick layer from Krakatoa. So we have an exact date on that Krakatoa eruption of 1883. Classic geochemistry didn't pick anything up. If you run ionic geochemistry, you can clearly signature those veins. So these ions have traveled through 1.5 meters of overburden in 100 years, over just over 100 years. So they do move fast and they don't spread. So it's a very powerful tool for looking undercover. We're starting to sort of, the geochemists are starting to use this and they'll be a little bit cleverer with the information now, and we're looking to signature certain deposits. So we can go like Simon would do in Los-Bronces. We would go and signature a known deposit. We can understand what those signatures are in various ratios of these ions, and then we can move outwards. This is an example of exactly that near Kurupeki in Serbia, where there's a known deposit just here. And we can actually start, if we look through the various ions, we can see a certain signature on that known mineralization. Again, classic geochemistry threw nothing out, but when we actually step out, we actually start to see some other areas that look particularly interesting and hence become drill targets very, very quickly. So that's ionic geochemistry, and I think it's fairly obvious as to why that's useful in exploring undercover. So how is the need or the move to exploring undercover going to change the exploration environment? So I think firstly, these aren't necessarily my points, these are just discussions that people have thrown out at me when we've discussed this. So successful explorers will be those who understand and embrace the concept of exploration search space. I think you can guess who said that, it was John Ronski, but the point of understanding is a business. He sees exploration very much as a business, and if you look at it in terms of if you're selling widgets, you know, how do you position yourself in the market? How do you position yourself in the exploration arena? It's by understanding this exploration search space and ensuring that you are the one dealing in that exploration search space. Juniors will have to rely on jurisdictional search space, first movers or frontier ground. That's often a concept now. John Varn from Anglo will tell you that juniors have to work in new jurisdictions. That's where they're going to find new deposits. Majors are going to find undercover. I'm not so sure that you necessarily agree with that, and I'll come to that just now. Increased depth of discovery and increased costs of working undercover will result in the return of the major explorers. What I mean by that is today most discoveries are found by junior explorers, with the majors gobbling them up afterwards and then exploiting those. Will that turn on its head in the near future, with the major explorers returning as, well, the majors returning as the major explorers? Does it have to be that? I don't know. This is why I think with successful adoption of things such as ionic geochemistry, mineral systems approach, machine learning, data science, we actually can make exploration more productive and cheaper. So I don't necessarily hold up that juniors are going to have to rely on jurisdictional search space. I think they can work undercover. Fast adoption of exploration innovation, concepts, technologies, and data integration, as I said, will allow juniors to play in this pond. That's my point. I think that if a junior really starts to think big, thinks undercover, does its homework, and uses some of these fairly low-cost tools to their benefit, they can still play in that field. We have to change and re-educate the junior investors to changes in exploration risk. I think that's a difficult one. We all know, those who obviously work in the junior market understand how the current junior capital raising is a broken system. And we are now looking more and more at non-traditional capital raising. And is there a way in which we can change our strategies or allow our investors to change strategies? The thing that majors have an advantage over juniors is that they can think in decadal strategies. Juniors can't. They need results now. Unless there's some way in which we can change that capital raising away to non-traditional approaches. And my last comment is, I think geologists are going to have to be brighter. I think we're all going to have to be more than just geologists. I think we're going to have to be data scientists, we're going to have to be mathematicians, we're going to have to be chemists. And like Antony, there's a disclaimer. So, okay.
Okay, thank you. Right, so now we have got 15 minutes before our food comes, I think it's the case. So, questions? Anybody got any questions for either of any of our speakers, or any comments? Points to discuss?
More.
Yeah.
you all talked about the mineral systems approach and how you can look at the larger lithospheric scale to try and help vector towards deposits and stuff like that. I was wondering if you know of any examples of where that's actually happened recently for a current mine or anything that's actually helped.
The most classic example of mineral systems approach working is Olympic Dam. There's a phenomenal image which I could probably show you of the MT data that shows this enormous fluid system that daylights directly underneath Olympic Dam, and it was one of those reasons that has led to that discovery and the subsequent discoveries since that. There's been a drill intersect earlier this year, which was I think it was probably one of the best copper drill intersects I've ever heard of, and I know where it was drilled, and it was drilled based upon a mineral systems model in that area. There's been some mineral systems models for the Barberton as well, which has led to some fairly new discoveries, but that exploration in South Africa is a different picture. There are a number of examples, but as I say, it's still relatively in its infancy in terms of it being used in anger. But again, some would argue that a lot of the discoveries found by Western mining back in the 70s were found due to this stepping away, not looking for the wood for the trees, and running a mineral systems approach to it.
Just to add to what James has been saying, it's true that Olympic Dam is by far the best example. I mean, in terms of more modern examples, a lot of the work has been done in Western Australia, because that's where a lot of the protagonists of this system have been based, and also you've got a fantastic data set available within Western Australia as well.
Yeah.
So another example in more recent times, if you the Gruyere gold deposit in Western Australia, for example, I think it was discovered in the mid to late 90s. That would be another example that I would suggest that you have a look at, because it was found using unconventional thinking, the mineral systems approach. So that's another one.
Less of a question, more of a comment. The oil and gas industry has kind of had that sort of approach to exploration for the last, ever since its inception. So there's probably a lot that we can learn from the oil and gas industry. From most of their stuff, all of it is undercover. It's that system of the source, transport, trapping, and then preservation. That's all pretty well understood in the oil and gas industry. So I think that this industry could certainly learn from that, and that's where the future could be.
I think it's a very fair comment, and the minerals systems approach is born out of the oil sector, definitely. But I mean, at university, I learned the whole source fluid trap thing, but it was never really utilised. It was never really practiced. It was like, oh yeah, I understand that, and now, this is a deposit model. That's what I'm looking for. I'm looking for this anomaly. Forget it. Think about the plumbing system and how does that fit? That's where it's coming from. And yeah, it's born out of success with the oil industry, and our industry is at least a decade behind, that's for sure.
I'm not a geologist, I'm like the guy at the other end of the process that makes the final product. But it seems to me that a lot of this is reactive data. All the information that you're gathering is based on existing operations, or close to, or below, or next to existing operations. So is there any sort of likelihood of using these algorithms and calculations and all this fancy mathematical analysis to actually grab hold of some data from, say, the USGS, the Geological Society, and say, look, I've got all this data that is on a database somewhere with one of these geological people, and apply this to that data and say, there we are, in the middle of Ashford, there's a fantastic possibility of a gold mine.
Absolutely, yeah, I mean, definitely. I mean, we're working with some of our clients on examples where there is very little exploration at all. Essentially, the main issues with the mineral systems approach is basically, it's all with any approach really, is the amount of data you've got at the start and the quality and format of that data. So where mineral systems has had a lot of success in Australia, because you've got an abundance of very good data, which is in the right format and can use it. It's people are now adopting it in areas which have less data. We're working with people in Central Asia, for example, who are doing this approach, and it's finding useful things. So there's no reason why you couldn't look in a more mature jurisdiction like America, for example, or Europe, to have a similar approach. There's no reason why it can't be used there. It's just traditionally, well, historically, I suppose, in the last 70 years, I guess less than that, the 40 odd years, I suppose, it's been used because the data is readily available. But there's no reason why it shouldn't be used elsewhere as well.
To answer your question, it is being done. That idea that you said, getting what data is and stuff, it's a fantastic example here. But you don't hear about it because it's all confidential. I've got several examples I can give you off the record, but I can't present them.
Okay, so it actually works then?
Oh yeah.
Okay.
With the ionic method, is there any caveats to it? So does it work to a certain depth and a certain kind of covering sort of deposits kind of obscure the data? And in which case, is there something that's complementary to the data? Like
I wouldn't say it's in its infancy. It's gone beyond its infancy, but we're still learning how to refine it. Russell Burrell is part of us, part of SRK now, and he's one of the guys who kind of coined the idea. Worked with the laboratories over many years, and he's still learning now, and he's well in his 70s. Depth-wise, we have seen positives again over known areas, so we know what we're looking at, to around about the kilometre scale. So we're still working on some of that. There's some difficulties in taking the sample. We've got to be, because you're talking about such small amounts, such slow detection limits, you've got to be very, very careful in taking the sampling. So one of the first things you have to do is ensure that none of the sample is smoke, for example, that you haven't got any sort of jewellery on you or anything like that, because biasing these results is very, very easy. So it's not just a simple, it is a very simple thing to sample to take, and you can take it as part of your classical geochemistry, but you just can't send someone out, any old person out there to do it. They've got to be trained to a degree because it is very sensitive.
Yeah, again, to add on to that, the actual technique itself of taking the samples is not that dissimilar from doing the standard soil geochemical survey. You just have to sample at a standard depth, make sure that all of the samples that you take are at a uniform depth over the area, but the collection, notwithstanding what James was saying about making sure that people don't smoke or wear jewellery or whatever, it's not that difficult, in all honesty. You just got to be careful with how you do it. But it doesn't require any specialist, I don't know, rock collectors or soil collectors or anything. You can use it using anything, really. You just have to be aware of not the limitations, you have to be aware of the issues that you could artificially introduce.
why would you need to have the same sampling depth for the data? Because if you had a regular erosion surface that's got deposit on top, if you sample at the same depth, you might have a good positive result somewhere, but then somewhere else that's actually overlying the deposit is then bad result.
You tend to run an orientation survey first and foremost, so you understand if depth actually plays any sort of role in it or not, and therefore, but you tend to end up just for best practices running the same aspect.
Just to add on to that, I think the best example I know of is North Mara in Tanzania.
Yeah,
And they highlighted it was like it was a bull's eye. And arcane greenstones underlying 200-300 meters of perlite.
Yeah.
Through MMI technology. And that was in the late 1990s, early 2000s.
Well, we're currently thinking about running it in some Central Asian examples, because it's had a very good run in Ireland, for example, in running in looking at some of that sedimentary hosted mineralisation at depth. And we've got clients in Central Asia who have an issue where they believe their ore deposit is extending in a particular way, but geophysics just can't pick it up, and it's expensive drilling, so they're not really sure, have we got an extension in this direction or not? So we're going to try geochemistry in that way.
So just one comment, the systems analysis now, the old adage of gold is where you find it. I think what you're saying now is gold is there, just go and find it.
Well, yeah, essentially.
Just further to your point there, I was involved in gold mining in the ANC based in the Sudan. Now, of course, as you just said, gold is there, but how do you find it? There obviously are in the south of Joburg and whatever, the whole territory has potential of gold sourcing. But I know in the ANC, gold is in a spasmodic relationship. Have you created is there a new mechanism now for being more specific about the location of gold on the ANC in particular?
I think in terms of yes, to answer your question, I think if you were to run a mineral systems model right across the Arabian Nubian Shield, I think you would, utilizing as much data layers as you can get. I mean, such things as seismic topography at say about the 200 kilometer level. That's a very good level to be looking at. Looking at the gravity as well, getting as much magneticity. I think you'd be really quite surprised at how you can center into camp scales that are completely being ignored. And I'm very confident that you'd find camp scales that have been ignored and are very prospective. Then when it comes to prospect scales, I think again there's some interesting discussions happening now, particularly on orogenic gold, in again moving away from this structural focus. And I'm not saying that structural geology isn't important. Of course it is important. But understanding that this deposit that you're looking at is a dynamic system, and that any structure that you're looking at has been mobilized and remobilized numerous times in different orientations, it's almost nonsensical to spend your time trying to assess that. And so looking for specific artifacts that sometimes get born out of this mineral systems approach can more rapidly focus you on a prospect scale as well. Again, there's a really good paper that just came out just this year discussing orogenic gold and the way that you should sort of reconsider the structural focus on it.
Thank you.
Cool. Well, I think any further discussion can be over wine and snacks, which sounds very, very good. Just before I close off, I would just like to big up IOM